Hi, today we are going to discuss about robot dynamics. First of all, what is robot dynamics? Robot dynamics deals with the mathematical formulation of the dynamic equations of a robot with its arm motion. It gives the relationship between forces and torques to the position, velocity, and acceleration of the manipulator. It can be used to compute the required forces and torques to attain a given position, velocity and acceleration of the manipulator. It can also be used to calculate the position, velocity and acceleration in response to given force and torque. First, how to find robot dynamics? How do we find robot dynamics for a 2D wave manipulator? In robot dynamics, it can be obtained by the two approaches. The first one is Lagrange-Euler formulation. The second one is Newton-Euler formulation. The Lagrange-Euler formulation LE is energy based, wherein the energy balance is utilized to obtain the dynamic model. Next one is Newton-Euler energy formulation. It is a force based, wherein the force balance is utilized to obtain the dynamic model. Lagrange mechanics, we call it as Lagrange function or Lagrangian. Here the L is defined as the difference between the total kinetic energy K and the potential energy P of a mechanical system. L equal to K minus P. The dynamic model can be found for any manipulator from this Lagrangian function L using the relation d by dt multiplied with dou L by dou Qi dot minus dou L by dou Qi equal to tau I, where Q is the joint displacement and Qi dot is the joint velocity of the I joint. Okay, we are going to discuss about dynamic model of a 2D wave manipulator based on Lagrangian mechanics. For the manipulator, the coordinate frames are 0 and 1, and the joint variables are theta 1 and theta 2. The link lengths are L1 and L2, and most of the links are M1, M2 and moment of inertia are I1, I2 respectively. Here the linear velocities are V1, V2 and angular velocities are theta 1 dot and theta 2 dot. Here we have two links L1 and L2. The coordinate frames are already we have seen the 0 and 1. Here the joint variables are theta 1 and theta 2. For link 1 it is theta 1, for link 2 it is theta 2. Most of the links for link 1 is M1, for link 2 M2. Why do we use X and Y here? Because we use Cartesian coordinate systems, so it is x1, y1 for link 1, x2, y2 for link 2. And also we have two velocities, linear and angular velocities. Linear velocity for link 1 is v1, for link 2 it is v2. Angular velocity for link 1 is theta 1 dot and for link 2 it is theta 2 dot. To calculate the Lagrangian function, the kinetic energy K and the potential energy P of each link is to be calculated, because L equal to K minus P in Lagrangian Euler formulation. For in this we have two links. First consider link 1. Consider link 1. Here the potential energy is given by P1 equal to 1 by 2 M1 G L1 sin theta 1. The kinetic energy is given by K1 1 by 2 M1 V1 square plus 1 by 2 I1 omega 1 square. It is considered as equation 1 and equation 2, where V1 equal to 1 by 2 L1 theta 1 dot omega 1 equal to theta 1 dot and I1 equal to 1 by 12 M1 L1 square. Here P represents potential energy, K is kinetic energy, P1 is potential energy for link 1, K1 is kinetic energy for link 1. Ms represents mass. Next, G is gravity, L1 for link 1, length of link 1, sin theta 1 for link 1, linear angular velocity of link 1. Here the linear velocity is v1 and v2. Substituting the values of v1, omega 1 and I1, we can get k1 equal to 1 by 6 m1 l1 square theta 1 dot whole square. Next, for considering link 2, we can get P2 equal to M2 G L1 sin theta 1 plus 1 by 2 M2 G L2 sin theta 1 plus theta 2. Here the kinetic energy is K2 equal to 1 by 2 M2 V2 square plus 1 by 2 I2 omega 2 the whole square. Here the velocity at the end of the link 2 can be found using the relation V2 square equal to x2 dot square plus y2 dot the whole square. We know that x2 equal to L1 cos theta 1 plus 1 by 2 L2 cos theta 1 plus theta 2 and y2 equal to L1 sin theta 1 plus 1 by 2 L2 sin theta 1 plus theta 2. Differentiating x2 and y2, we get minus L1 sin theta 1 multiplied with theta 1 dot minus 1 by 2 L2 sin theta 1 plus theta 2 multiplied with theta 1 dot plus theta 2 dot. Here y2 dot equal to L1 cos theta 1 multiplied with theta 1 dot plus 1 by 2 L2 cos theta 1 plus theta 2 multiplied with theta 1 dot plus theta 2 dot. Here omega 2 equal to theta 1 dot plus theta 2 dot and I2 equal to moment of inertia 1 by 12 M2 L2 square for link 2. So we calculate the kinetic energy for link 2 as 1 by 2 M2 L1 square theta 1 dot square plus 1 by 6 M2 L2 square theta 1 dot plus theta 2 dot the whole square plus 1 by 2 M2 L1 L2 cos theta 2 multiplied with theta 1 dot square plus theta 1 dot multiplied with theta 2 dot. For link 1 we have K1 equal to 1 by 6 M1 L1 square theta 1 dot square. For link 2 K2 equal to 1 by 2 M2 L1 square theta 1 dot square plus 1 by 6 M2 L2 square multiplied with theta 1 dot plus theta 2 dot plus 1 by 2 M2 L1 L2 cos theta 2 multiplied with theta 1 dot square plus theta 1 dot theta 2 dot. So it's the time to calculate Lagrangian. The Lagrangian is given by L equal to K minus P. Here K equal to K1 plus K2 for link 1 and link 2. P is P1 and P2, so K1 plus K2 minus P1 plus P2, it is equal to K1 plus K2 minus P1 minus P2. Substituting the equations of K1, K2 and P1, P2, we can get L equal to 1 by 6 M1 L1 square theta 1 dot square plus 1 by 2 M2 L1 square theta 1 dot square plus 1 by 6 M2 L2 square multiplied with theta 1 dot plus theta 2 dot the whole square plus 1 by 2 M2 L1 L2 cos theta 2 multiplied with theta 1 dot square plus theta 1 dot multiplied with theta 2 dot minus 1 by 2 M1 G L1 sin theta 1 minus M2 G L1 sin theta 1 minus 1 by 2 m2 g L2 sine theta 1 plus theta 2. So from this we can extract the torque tau 1 equal to d by dt dou L by dou theta 1 dot minus dou L by dou theta 1. Substituting the equations of L, K1, K2, P1 and P2, we can get the torques tau 1 and tau 2. It represents the motion of a 2D manipulator arm. It is also called as dynamic model of a 2D manipulator arm. It can be observed that this technique is complex just for a simple 2D manipulator. Finding the dynamic model for higher DOF manipulator arm would be even more complex. Hence, a generalist approach called Lagrange-Euler formulation is followed. The Lagrange-Euler formulation consists of 8 steps. It is a systematic procedure for obtaining the dynamic model of an NDOF manipulator. This Lagrange-Euler formulation establishes the relationship between joint positions, velocities, accelerations, and the generalized torques applied to the manipulator. The equations of the motion obtained are analytical and compact. Already we have seen the dynamic model of 2D manipulator as tau 1 and tau 2 in terms of L1, L2, K1, K2 and P1, P2. The matrix vector form of equations is appealing for calculations and control system design. In Lagrange-Euler dynamic model algorithm consists of 9 steps. The step 1 is assigning frames using Denavit-Hertenberg notation. Step 2, obtain link transformation matrix. Step 3, consider either revolute or prismatic joint. For step 4, determine the inertia tensor II. Step 5, compute Dij. And step 6, compute the inertia coefficients. And step 7, compute velocity coupling coefficients. Step 8, compute gravity loading terms Gi. And finally, substitute all the coefficients. We can get the dynamic model of 2D manipulator. It is called as tau I. Thank you.